Let's continue our discussion with a discussion of the Doppler effect. The Doppler effect is essentially what happens because when a moving object emits a sound, the velocity of the sound is a combination of the velocity of the object and the velocity of the sound. And this in turn results in a change in the frequency of the sound depending on whether the object is moving toward the observer or away from the observer. So let's take a look at this situation. You have two individuals, X and Y, and a sound being emitted toward both of them. This change in frequency is known as the Doppler shift. It's an alteration in the observed frequency by the observers due to motion. Now this motion can either be the motion of the source, a motion of the observer, or in more complex situations, a motion of both. Sound is emitted by a source and it is emitted in spherical waves. Because the source, observers, and air are stationary, in this case, the frequency and wavelength are the same in all directions to all observers. So everything is stationary here, so the frequency and the wavelengths do not change. However, if you have a situation like pictured here, you have stable or stationary observers, but the source is traveling from X to Y. In that case, the sound emitted by the source is while the source is moving from left to right, spreads out as you can see in this diagram. And you can see what occurs is that the wavelengths on the side of X become longer and longer, while the wavelengths on the side of Y become shorter and shorter. And this in turn causes a shift in the frequency because the sound velocity does not change. So the observer at Y hears a higher pitched or higher frequency sound. The observer X hears a lower frequency or lower intensity, not intensity, that's not the right word, lower frequency or lower pitch sound. And so this occurs even though the frequency actually being emitted does not change, and this is known as the Doppler shift. And it's calculated as follows. In a situation where the source is moving, so the observers are not moving, the source is moving, the observed frequency is equal to the emitted or source frequency times the velocity of the wave divided by the velocity of the wave plus or minus the source. Now, how do you determine whether it's plus versus minus? Well, if the source is moving toward the observer, then it's minus, making the denominator smaller, making the observed frequency higher. If it's moving away from the observer, then it's a plus, making the denominator larger, making the observed frequency lower. So in this situation, with the source moving, if the source is moving toward the observer, then it's a minus. If the source is moving away from the observer, it's a plus. Now here we have a situation where the source is stationary, but now the two observers are moving. X is moving away from the source, Y is moving toward the source. The same effect can be produced if the observers move relative to the source. The motion toward the source increases the frequency as the observer on the right passes through more wave crests than she would if she were stationary. The motion away decreases the frequency because the observer on the left passes through fewer wave crests than if he were stationary. And the formula is given here. Now you notice now that instead of being in the denominator, it's now in the numerator. So the observed frequency is equal to the source frequency times the velocity of sound plus or minus the velocity of the observer divided by the velocity of sound. Again, if the observer is moving toward the source, it's plus, giving you a bigger numerator now and a higher pitch. If it's moving away, it's minus, giving you a smaller numerator and a smaller frequency. So it's important to try to relate it whether you're moving toward. You're always going to end up with a higher observed frequency, and you can think through the signs if you use that logic, and we can talk about that in class as well. So let's take a look at a couple problems. Suppose a train has a 150 hertz horn and is moving at 35 meters per second in still air on a day when the speed of sound is 340 meters per second. What is the frequency observed by a stationary person at the side of the tracks as the train approaches and after it passes? What is the frequency observed by the train's engineer that's traveling on the train? So in this case, we have a source that is moving and a single observer who's stationary as it passes. So the formula, remember, for the source when it moves is as follows. So the observed frequency is equal to the source frequency times the velocity of sound divided by the velocity of sound plus or minus the velocity of the source. Now in this case, we'll start out looking at toward. Now when the source is moving toward, this is a minus, okay? So we have 150, which is the source frequency, times 340 divided by 340 minus 35. And if we do that, we get 162 hertz. So it goes from 150 to 162 hertz. If we're moving away now, after it passes the person on the tracks, it's now going to be 150 times 340 divided by 340 plus 35, which is going to be 136 hertz. Now the last part of this is kind of a trick question, because if he's on the train, he's moving with the train, so relative to the train, he's stationary. So he would hear the sound as it is being emitted. Now the second problem says a spectator at a parade receives a observed frequency of 888. So F observed here is going to be 888 hertz. From an oncoming trumpeter whose source is going to be 880. And the question is, what is the speed of the musician if the speed of the wave is 338 meters per second? So again, it's the same. The source again is moving. So we have F observed is equal to Fs times VW over VW. And in this case, again, it's moving towards, so it would be minus Vs. And in this case, let me make this a little clearer here. In this case, since he's moving toward the guy, it's going to be a minus sign here. Now let's look at how we would do this. We end up with Fs VW is equal to F observed times VW minus Vs. And then divide both sides by observed, and we have VW minus Vs is equal to Fs VW over F observed. And then to get the velocity of the source, we just subtract VW, and what's going to end up happening here is it'll be in the negative, and then negative will work that out. So VS, negative VS, is going to be the frequency of the source, which is 880, times VW, which is 338, divided by observed, which is 888, minus 338. And you can see that you're going to get a number that's a minus number, because this here is less than 1 times this, and what it ends up being is 3.05 meters per second. Let's move on now and talk about sonic booms. Sound that travels from a source that is moving faster than the speed of sound spreads out, like you see in this diagram here. It spreads out spherically, but the source moves ahead of each emanated sphere. Because of constructive interference along these lines, it's actually a cone, as it says here, because it's doing it in 3 dimensions. There's a shock wave that's produced, and that shock wave is called a sonic boom, and this occurs when the speed of the source is faster than the speed of sound. And the faster the speed of the source, the smaller the angle theta is. You can have 2 sonic booms, one created by the nose of the plane and one created by the tail of the plane. And they're actually observed differently by passers-by. Another thing that sound can be used is is what's called sound canceling or noise canceling headphones. Noise canceling headphones use constructive and destructive interference to cancel out outside noises. And here's the diagram showing how this works. The headphones are designed to cancel noise by emitting a sound that's like the outside incoming sound but opposite in wave. These are much more effective than what's known as passive attenuation, which is just shoving an ear plug in your ear. And these headphones are used in very high risk situations, like the example given here is the Voyager aircraft, because of the engine noise. Now we're going to talk about, and I want you to spend a little bit of time looking at the book and thinking about this, because this can be a little complicated to understand, but we're going to talk about the impact of interference and resonance. Now resonance can move through 2 types of tubes. One is an open tube and the other is a closed tube. And you'll notice that I emphasize the word closed here because all of the calculations and formulas are different when you're dealing with an open tube versus a closed tube. So whenever you read a problem about this, make sure you understand whether you're dealing with an open tube or a closed tube. So the next several slides we're going to look at, we're going to be dealing with a closed tube. And what happens is that when you put a tuning fork close to the opening of a closed tube that's closed on the other end, the wave travels down to the closed end and then reflects back to the source. Now the point where it enters is called the node because it's the point of smallest, and the point where it reflects off the back is called the antinode. It's the maximum air replacement of the standing wave. Now once it reflects back, it does the same sort of thing. It disturbs the air coming back. The disturbance then is reflected, and you have waves coming in from the tuning fork. At the same time, there are waves returning from the back of the tube because it's a closed tube. The resonance of the air in a closed tube is caused by a tuning fork. If the length of the tube is just right, and this is what's important, the disturbance gets back to the tuning fork half a cycle and interferes constructively with the incoming wave that's being generated by the fork. And this interference causes a resonant sound. And when you do this in the lab, basically the way we did it in the lab when I was in high school is we put water in a tube and we would hold it over and we would change the level of the water. And when you actually reached this point where the length was perfect, the tube would begin to hum very loudly. Now the resonance, when you do this graphically and look at it, the length of the tube, at that point when this resonance happens, the length of the tube corresponds to 1/4 of the wavelength of the wave. And I'll show you a picture of why that is. And the resonance that occurs is called the fundamental frequency. And the tone that you hear is the fundamental frequency. So here you have an example of what's shown as the fundamental frequency. And you can do this more than one way, and you can see why it's 1/4 if you look at the entire wavelength being all the way to here. Okay, so the point at which this bounces off the back wall and you entry and exit is the same is right here, and it's 1/4 of the total wavelength. And as you can see, if you can have another length where you have again the antinode right at the point where it's entering the open side of a closed tube, and this is going to be 1/2 plus 1/4 or 3/4 of the wavelength. And this is called the first overtone. And this shows in a closed tube session the fundamental and the first 3 overtones. And you can see what happens here is at each point where the length is equal to the antinode. So you have 1/4, 3/4, 1 plus 1/4 or 5/4, 1 plus 3/4 or 7/4, and that's shown right here. So in each case the length gets longer and longer, okay? But then also you see the frequency is calculated. You start out with 1/4 of V over L, then it's 3/4 V over L, then it's 5/4 V over L, and 7/4 V over L. And that's what you have to remember. And then this calculation up here just changes the frequency, the wavelength of what you're going to hear. Now the throat is a closed tube, and it resonates that way. The spectrum of overtones and their intensities are then shaped by the mouth and the tongue. And you can actually, we commonly do this in people with laryngeal cancer. We have to take their voice box out, and therefore you can still have speech by emitting a sound that they can basically fluctuate with their mouths. Now, this diagram changes to the open tube. So this is open in both ends. So there's no reflection at this point. So the resonant points are the points where the 2 antinodes are at the 2 open ends, which is 1/2, 1, 3.5, and 2. And you can see how that works here. So that's why I said it's extremely important to know whether you have an open tube or a closed tube, because the calculation is different. String instruments basically take advantage of this, and they put the strings over the vibrating box, which is a form of closed tube. And the string then vibrates, and when it causes it to resonate. So here's a problem we can work. What is the fundamental frequency of a 0.672 long tube open at both ends? Important. On a day when the speed of sound is 344. What is the frequency of its second harmonic or its second overtone? So let's take a look at that. So first of all, we need to write down that the velocity of sound here is given as 344. The tube length is given as 0.672 meters. We are dealing with an open tube here. Therefore, we have to use the formula for the open tube, which is shown right here. And the fundamental frequency is equal to V over 2L. So FF is equal to V divided by 2L, which is equal to 344 divided by 2 times 0.672, which is equal to 256 hertz. And the second overtone is right here, 3V over 2L. I'm sorry. That's going to equal 3 times 344 over 2 times 0.672. And that's going to equal actually 3 times this number, which is 768. Now let's look at another problem, very similar problem. Resonance has been used for musical instruments since prehistoric times. This marimba uses gourds, notice that they're closed, as resonant chambers to amplify the sound. So here's a pipe organ that's closed at one end and produces a fundamental frequency of 256 with the air temperature of 18 degrees. What is the fundamental frequency at 25 degrees? So first of all, you're going to have to find the length. Then you find the frequency at 25 degrees. So let's take a look at what we know here. First of all, we have to calculate the velocity. It's going to equal 331 times the square root of t over 273. And we put t in as 291, the new temperature, over 273. And that's going to equal 341.7 meters per second. It's a closed tube, so now F is equal to V over 4L. And we arrange this to find L. We get L is equal to V over 4 times the fundamental frequency. And so that's going to be 341.7 divided by 4 times the fundamental frequency, which was 256. And we get a size of 0.334 meters. Now we have to calculate, so that's the first answer. We have to calculate a new velocity at a different temperature, because they want to see what happens to the fundamental frequency if the temperature goes up to 25, which is 298 divided by 273. And that gives you a new velocity of 345.8 meters per second. The fundamental frequency then is equal to this velocity divided by 4L, which is equal to 345.8 divided by 4 times L, which is 0.334. And that gives you a fundamental frequency of 259 hertz. So it changes by 3 hertz with a change in temperature like that. And that's important to remember. And that's why when musicians tune their instruments, you'll see them changing the length of their instruments. And that, like a trumpet or clarinet, and that is based or frequently is affected by the temperature in the room at the time that they're doing their